Hello everyone and welcome to another lecture series on measure theoretic probability. So today in lecture 6 we will be talking about the uniqueness of the extension. So remember that you know that there exists some kind of extension, and this extension, if we define a measure on a field, we can actually uniquely extend it to a sigma field generated by that class. So here we talk about the uniqueness aspect of it. What do you mean by the uniqueness? If you have two measures and they agree, then implies that these measures are what? Very unique, and you can actually uniquely extend it from a field to what? A sigma field. And we talk about a machinery that will help us extend this field measure from what? A field to a sigma field. So we talk about the Denkin pi lambda theorem. We state that if you have a class P, which is a pi system, and a class L, which is also what? A lambda system, and P is a subset of this class L, then the sigma field generated by P is a subset of is a subset of what? Of L. That's what the pi lambda theorem tells us. So we are going to use this machinery to extend our P measure uniquely to the sigma field generated by it. So we define P on a simpler class as a field, and by the Denkin pi lambda theorem we will be able to actually extend this P measure uniquely to the sigma field generated by it. Note, since a field is a pi system, the uniqueness in the existence and extension theorem is a consequence of the following result. So theorem: suppose we have P1 and P2 being being probability measures on the sigma field generated by the class P, where P is a pi system. If P1 and P2 agree on the class P, then they agree on the sigma field generated by what? This class P. So this brings an idea out of the what? Of the Denkin pi lambda theorem. Alright. So remark, the result remains true for sigma finite measures. So here we consider a case of what? The probability measure. Okay, so we prove this theorem. So we consider a class, and this class we label it as what? Class L. And this class is a collection of what? Elements in the sigma field generated by what? P. Note, P is what? It's a pi system. So it suffices to show that L is what? It's a lambda system. If you're able to show that L is a lambda system, then by the Denkin pi lambda theorem, we conclude that the sigma field generated by P is a subset of what? Of L. And note that P is a subset of what? Of L. And in this class, we define that P1 and P2 agrees on the elements of what? Of this class. So this tells us about the uniqueness aspects of it. So by condition 1, for this class to be a lambda system, then we need the whole space to belong to what? To that class. And if the whole space belongs to that class, then we know that P1 and P2 has been defined in that class. And if any element belongs to that class, then P1 and P2 should be equal. So if you take the whole space to belong to L, then it implies that P1 on the whole space should be equal to P2 on what? On the whole space. And they all give us what? 1. So it's ticked. Hence, P1 indeed belongs to what? L. By condition 2, so we are just proving that L is what? Is a lambda system. So we are satisfying the conditions that it needs to what? Is to be a lambda system. By condition 2, we are saying that if you have A belonging to L, then A complement should also belong to L. But before this to be true, then remember that as we defined early on, P1 should agree to P2 for any A that belongs to what? To L. Okay, so we are saying that, okay, then P1 of A complement should be equal to 1 minus P1 of what? Of A. Remember that A belongs to L. So this is equal to 1 minus P2 of A. Remember that the class L, for any A belongs to L, P1 should be equal to what? P2. So if A belongs to L and we have 1 minus P1 of A should be equal to 1 minus what? P2 of A. And hence this can be rewritten as P2 of what? A complement. And hence we have what? P1 A complement is equal to P2 what? A complement. Therefore, A complement belongs to what? To L. A complement belongs to L. A complement belongs to L. Then we move on to the last condition for this class to be what? To be a lambda system, and therefore we uniquely extend our P measure to a sigma field. Interesting. Okay, so by condition 3, for L to be what? A lambda system, if you have AN that belongs to L are disjoint sets in L, then we know that the accountable union should also belong to L. So we need to show that the accountable union belongs to L. And if that's supposed to happen, then P1 of the accountable union should be equal to P2 of what? The accountable union. But how do we do that? First, remember, P1 of the accountable union of AN should be equal to the sum of their individual P1 what? Measures by condition 3 of probability. Since ANs are disjoint, then by countable additivity, if you have probability of the countable union of AN, it should be equal to what? The sum of their individual probabilities. So we apply that condition here and note that AN belongs to L. So this implies that P1 of AN should be equal to what? P2 of what? Of AN. And we can rewrite this back to what? P2 of the accountable union. And therefore we've proven that P1 of countable union of AN is equal to P2 of the countable union of AN, and hence then the countable union of AN belongs to what? To L. So here we deduce that the lambda 1, lambda 2, lambda 3 implies that L is a lambda system. And by hypothesis, we know that the pi system is a subset of what? Of the lambda system, because P1 and P2 agree on what? On P. And therefore the sigma field generated by what? By this pi system is a subset of what? Of the lambda system. That is what the pi lambda theorem tells us. All right. So note, there's some interesting outcome here. Remember, by condition 3, the lambda 3 was what needs for axiom 3 of probability measures to hold. So note, the pi lambda theorem and the concept of the pi system are exactly what is needed to make the proof work. One of the essential properties in the definition of the probabilities is the countable additivity. Remember, by condition 3, the axiom 3 of probability measures, we need disjointness in what? In the elements, such that when you take the probabilities of the accountable union is equal to the sum of their individual what? Probabilities. So this is exactly what is required on lambda 3. So lambda 3 needs disjointness in its elements, and this helps us uniquely extend a P measure from a field to a sigma field uniquely, because if we define any two measures, they agree on the class that we are talking about. Okay, so this is the uniqueness of the extension that you've been looking for, and thank you, or see you on lecture 7. All right, bye.